Hello everyone, welcome to the 23rd lecture in this series. In today's lecture, we are going to study about threaded binary trees. Hope you remember what we learned with the previous lectures. We have been studying about tree data structure in specific. We learnt various terminologies associated with trees, and then we dived into learning binary trees and the various traversals that are permissible in a binary tree. In today's lecture, we are going to see a kind of binary tree which is a threaded binary tree. I hope by this time you remember the definition for binary trees. A binary tree is one which can have a maximum of 2 children, and otherwise it can even have, every node can have even one child, and it can even be a node with no children. So, in case of node with 2 children, it is fine that every node will have 2 pointers pointing to each of its child. If in case if it is a leaf node with no child, then we will have the node to have null pointers with it. So, its left and right pointers will be having a value of null. So, here we are thinking of improving the performance of a binary tree in specific to traversals. We are thinking of in-order traversals. So, in case of in-order traversal, always there is a possibility for us to get a sorted list of elements. So, when we look for in-order traversal, we normally make use of a stack, and you know very well that when we go for stack implementation, it is going to be a bit tedious. And so, in order to improve the performance of binary trees and avoid wastage of space by null pointers, we are going to put the node's successor as well as predecessor in the place where we store null values. So, that is we are going to study in detail with respect to this threaded binary trees. Now, we are going to study the standard definition for a threaded binary tree. Let us consider this example. So, in this example, as you see, we have a binary tree because every node has 1, 0 or 2 children, and here you could see that you could see some dotted lines and some thick lines. So, the thick lines are all pointers to children, and the dotted lines are what we mean as threads. So, here what we actually mean as threads is that instead of storing null values on nodes, the null values are replaced by pointers to successors or predecessors of a node. So, this greatly simplifies traversal, because as you know, consider that we perform a in-order traversal. If in case we think of doing in-order traversal in this tree, we will start from the root. The order for doing in-order traversal is we have to visit the left subtree, then the root node, and finally the right subtree. So, we will start with F. We check whether there is any left subtree, there is, and so we move to B, and we check whether there is any left subtree, and so we move to A, and from A there is no other left subtree. So, we start our traversal from here. So, A is the first node visited as a part of in-order traversal. After visiting A, we may have to move to the right subtree of B, which is D. In order to facilitate that, we have to backtrack and go to D. So, here for the sake of visualizing this backtracking, we have to employ a stack. So, that is what we are replacing with this threaded binary tree. Instead, what we do is that as node A's right pointer is free and having a value of null, we are going to replace it by the value of its successor, that is A's successor is going to be D, right. So, that is how in here the A successor is B, and so we are going to have a pointer to A. So, this is what the replacement we actually make with the help of threaded binary trees. So, if suppose a node's right child pointer is null, then we put up the node's successor there, and if suppose a node's left pointer is null, then we put up the node's immediate predecessor. That is the way we organize a threaded binary tree, and the putting the pointers to successor and predecessor is what we mean as threads, and so this tree has got the name threaded binary tree. So, the advantage we gain with threaded binary tree is that threaded binary tree actually makes the traversal very faster, just because it does not employ a stalk and we do not do recursion for performing a traversal operation. So, these are some things that are true for a threaded binary tree. So, binary trees generally waste a lot of space, and for implementing binary trees, when we consider a linked representation, every node has to have 2 pointers and 1 data field. So, here we are thinking of a way to utilize the space better. So, we store a special pointer that points to nodes higher in the tree or nodes that are following this particular node, that is what we mean as predecessor and successor. So, here what we mean is we are talking about one threaded tree, and so we say that we are making the null values to be replaced by nodes ancestors. So, that greatly helps us with in order traversal. So, the special pointer, that is pointer to ancestor, we call as special pointer, and that is what we mean as threads. And when a tree has threads, then we call such a binary tree as a threaded binary tree. And we need to know whether a pointer is actually a pointer to a children node or a pointer to a thread. So, in order to differentiate this, we are going to maintain special variable or flag. So, that flag will distinguish a pointer, that is a normal pointer, and a thread. So, normal pointer is pointer to children or child, and thread is what we mean as pointers to ancestors. So, these are the two types in threading. One is one way threading and other one is two way threading. So, in case of one way threading, a thread will normally appear along the right pointer, that is the pointer to the right child, and that is I mean whenever we have a pointer or a thread in this fashion, that greatly helps us with in order traversal. And so, when we want to speed up in order traversal, normally we go for one way threading, and that too at the right side. And we have other way of threading which is called as a two way threading. So, in case of a two way threading, we will be having threads in both right and left sides. So, as I said before, the left thread would point to immediate predecessor and right thread would point to immediate successor. So, when we have a two way threaded tree, that helps us to navigate trees in both the directions, because we have pointers flowing in both the directions that can take us either in the forward direction and as well as in the backward direction. So, these are the types of threaded binary trees which you find normally with many of the textbooks. So, one is a right threaded tree, other one is a left threaded tree, and we have a fully threaded tree as well. So, first let us see what right threaded tree means. So, here as I said, we will be replacing null pointers in the right child, I mean nodes right child pointer will be replaced by a thread to the successor, and that helps with in order traversal. And so, the tree has the tree has got the name as right threaded tree. Alternatively, we can even make use of nodes left pointer if in case it is null. So, that can be replaced by a thread, and the thread will be to the predecessor, and that is what we mean as left threaded tree. And the third way of doing is that we can have threads along left and right child pointers, and if so, we call the tree as a fully threaded tree. And if the other name for a fully threaded tree is two way threaded tree, and left threaded tree and right threaded tree fall under the category of one way threaded tree. So, here is an example of how a one way threaded binary tree would look like. So, we just look at pointers, the right child pointers that are all null. So, here you could observe that 30, 50, 69, 30, 60, 69 and 80 or all of them are leaf nodes, right. And here there is one intermediate node 50 which is also having only one child, and that too it is a right child, right. So, here we are focusing only on leaf nodes, and leaf nodes right child pointers, if they are all null, we are going to replace with threads. and the threads are nothing but pointers to their immediate successor. So, after visiting 30 in order traversal, we may have to backtrack and move to 40. So, that is what we mean as immediate successor. So, this thread is pointing to its immediate successor, which is 40. So, threads are all shown as dotted lines, and thick lines refer to the actual normal pointers that are pointers to children or child nodes. And so, here we have a pointer from 60 to the root node, because 60 happens to be the rightmost node in the left subtree, and its immediate successor naturally becomes the root node, and so there is a pointer to the root node which is 65. And similarly, we have a pointer to immediate successor from 69, which is 72. And as you see here, the node 80 does not have a thread, just because it is the last node in the binary tree, and that too this node will naturally does not have any successor, and so it is left empty. There is no thread put up there. So, now let us see how we can do this modification on a threaded tree. So, instead of wasting pointers by storing value as null, we just add threads, and we think that adding threads greatly simplify or reduces the complexity when we perform a in order traversal and avoids backtracking. So, here you could see that all the leaf nodes, they are supposed to have null values, and all of them are made to have or store threads which are predecessors or successors, whatever it be, whether it is left or in the right side. And as you know, node 1 and 13, though they are leaf nodes, node 1 does not have a predecessor, and so its left thread is absent, and node 13 does not have a immediate successor, and so its right thread is left blank or retained as null. Now, let us see how a two-way threaded binary tree would look like. So, in a two-way threaded binary tree, as I said, both left and right child pointers, if they are null, they are made to store the values of threads which are immediate predecessor and immediate successor respectively. So, here in this case, you could see that node 30, 60 and 80 and 69 are all of them are leaf nodes, and see with respect to 60, it is made to store two threads, one pointing to its immediate predecessor which is 50, and one pointing to its immediate successor which is 65. The same is the case for node 69, but you could see that nodes 30 and 80, they do not have left thread and right thread, just because they do not have immediate predecessor and immediate successor. The same we have explained here. Node 30 does not have an in order predecessor, because it is the first node when we do a traversal in, and that too an in order traversal, and 80 does not have an immediate successor, and that is why it is left blank or retained as null. This is an alternate way of representing a two-way threaded binary tree. So, apart from the tree with 65 being the root node, we have a header node. So, this header node we have already learnt with the linked list. So, always the header node will point to the first node in a linked list. Similarly, here we have put up a header node. The purpose of the header node is to point to the root node of the tree. So, naturally this header node will have the address of the root node, which is the address of node 65. And in that particular header node, you could see that its left pointer only points to the root node, and its right pointer is made to point itself. So, this is how we implement a two-way threaded binary tree with header. So, always we create a dummy node. So, we mean it as a dummy node because it is not going to have any data value, only its left child pointer is going to point to the root node, and its right child pointer is going to point to itself. And here you could see that same, the threaded binary tree is represented as the left child of the header node, rest of the things are one and the same, and the right child pointer is made to point to itself. And here there is one variant you could observe. So, as I was mentioning with the previous example, that in case of two-way threaded trees, 30 and 80 will not have any threads, just because they do not have any predecessor or successor, right. So, here if we make use of this header based implementation, then what we could do instead is that 30's left child pointer could be made to point to the header node, and 80's right child pointer can be made to point to the header node. Thereby, we are able to traverse this particular tree in both the directions, and that is the very purpose of including this header node. Now, let us see how to represent this threaded binary tree, how the node structure should actually be. So, there is a slight change in the node structure just because we are going to have threads in addition to pointers. So, as I was mentioning in one of the earlier slides that we need to have a way to differentiate a normal pointer and a thread, and so for the differentiation sake we have added two flag variables, and that is why this node structure looks expanded. So, in a standard way of doing, we will have one data placeholder and two address holders, right. So, here in addition we have two flags to denote whether it is a thread or not. So, you have two fields named left thread and right thread, and they may take up two values, either 1 or 0. If it is 1, it indicates that it is a normal pointer, which means it is a pointer to a child node. If it is 0, means it refers to a thread, and so if it is on the left side it would point to the predecessor, if it is on the right side it would point to the successor. So, that is the change in the node structure with respect to a threaded binary tree. So, here you see the standard way of defining the node structure using struct statement. So, here you could see that the structure's name is node type, and this structure has two self referential pointers. So, one is left and right. So, this is the standard way of defining a tree using a linked representation. But here the only other difference is we have one more flag variable. Here in our case it is thread. So, it is the structure definition for a one way threaded tree, just because we have only one flag variable, and we can assume that this thread always points to the immediate successor to facilitate in order traversal. And as I said before, this thread can take up only two values, either 0 or 1. If it is 0, then it means this thread is normal pointer. If it is 1, it is actually a thread and points to the successor. So, here we see an example where we have a one way threaded tree and it is a right threaded tree. And so, since it is a right threaded binary tree, you could see only threads along the right side on the leaf nodes. So, 1 is a leaf node and it has a thread along the right side. 5 is a leaf node and it has a thread along the right side. Similarly, 7 and 9 are all leaf nodes and they have threads along the right direction. So, this is how your one way threaded tree would look like. So, now let me explain how this threaded binary tree simplifies in order traversal. In case we had implemented this as a binary tree, then for doing this in order traversal I should come down till 1, then backtrack and go to 3, because after 1 there is no other nodes here. So, we should backtrack to 3. So, in order to eliminate the use of stack, here we have maintained threads. So, after visiting node 1, I go along the forward direction, which is 3 in this case. So, you need to put in mind here that normal traversals always start from the root node, but in case of a threaded binary tree traversal we always start traversal from 1. So, we initialize our pointers to point to the leftmost child on the left subtree. So, naturally 1 would be our starting point, and after that 1 has a thread to 3. So, we naturally visit 3 and then we move to 5, and from 5 we have a thread to 6. So, we visit 6, and from 6 there is a forward pointer, that is a normal pointer to 8. So, visit 8. From 8 we visit 7 because we have a normal pointer between 7 and 8, and then we have a thread from 7 to 8, and from where we move forward along 11 and then 9, and then there is a thread that takes up to 11, but 11 is already visited, So we have to go to 13. But the standard way of doing is that we start from 1, go to 3, 5, 6, and then we are going to 8. But as you know, this is a forward pointer, and that too it is a normal pointer. So we don't put 8 in the output, rather we go along till 7. We then mark 7 as visited, followed its thread to visit 8, and then only we mark 8 as visited. So only then we will be able to get that in order traversal, and you know that it is a binary search tree, and so its output should be in sorted form after performing a in order traversal. So that is the reason why we add up a check condition here, that we take up this path and follow this, and then only we mark 8 as visited, and rest of the things are similar. And finally we have the output of this form, that is 1, 3, 5, 6, 7, 8, 9, 11 and 13, which is actually in sorted order. So this is one sample code for threaded binary tree traversal. So here this is a function that takes you to the or positions the pointer to the leftmost node. So we start with the root node n, and we check whether it is null. If so, we return null. Otherwise we do go to the bottommost position on along the left subtree. So we check whether the left subtree of node is not null. If not null, we navigate to its left subtree. That is why how we position the pointer to the leftmost node, and followed by that we actually implement this loop. So we check whether current is not equal to null. If not null, we print the particular value. That is what we did with the previous example. And then after printing the particular node's data value, then we check whether there is any write thread. If so, we go along the write thread. Otherwise we just position our pointer along leftmost node along the current node's right subtree. So that is how we perform in order traversal with the help of this threaded binary trees. So you should keep in mind that when we go for threaded binary trees, we completely eliminate the use of stack, and we don't follow any recursion, and we don't do any sort of backtracking. We completely rely on threads to perform traversals on a threaded binary tree. So to summarize what we have seen so far with threaded binary trees, so the very purpose of this threaded binary tree is it optimizes or greatly enhances the in order traversal by replacing null pointers with threads. And so we don't use recursion here, and we don't use or employ a stack here. And we have two types of threaded binary trees. One is a single threaded binary tree. In case of single threaded binary tree, you could make use of the spaces available along right child pointer or left child pointer, and more often we use the right child pointer just because that helps us to locate the in order successor, which is very necessary for in order traversal. And in case of double threaded trees, as you know, you make use of both the child pointers left and right to store predecessor and successor respectively. And when we talk about traversal efficiency, in order traversal can happen with order of n, where n happens to be the number of nodes in your tree, and that too the space complexity would be of the order of 1, and we don't use any recursion or stack. And the advantages is that this threaded binary tree eliminates wastage of space, just because we avoid storing null values. Instead we store threads in that place, and it speeds up the traversal process, and in a constrained environment it helps to improve the efficiency, and it finds application in many domains, like it is used in database indexing, it is used with compiler design, and it also is used with any sort of memory efficient tree traversals. Now I have put up some questions to test our understanding of the concepts of threaded binary tree. One is, what is the main advantage of a threaded binary tree over a normal binary tree? So in a normal binary tree, you know, we actually waste space with storing null values on pointers to left and right subtrees in a leaf node, whereas we avoid that with threaded binary trees, and instead we use that space to store threads which are predecessors and successors to node, and that serves to be an advantage in specific to traversal. And what are the two types of threaded binary trees? You know, it is one way threaded and two way threaded, and two way threaded is also called as fully threaded binary tree, and one way threaded could be either right threaded tree or left threaded tree. And how does a threaded binary tree improves in order traversal? So, in order to do in order traversal on a binary tree, we may have to go down the tree along the left subtree to take the first node, and then we have to backtrack and visit the right subtree, and we may have to do this for every node, right? And that is eliminated in a threaded binary tree because it has threads. So, we always move along the forward direction looking for successors along the binary tree. And what is the time complexity of in order traversal in case of a threaded binary tree? It is going to be the size of the tree, which is the number of nodes in the tree. And so, in our case the time complexity would be of the order of n, where n is the number of nodes in the binary tree. So, when it comes to real world applications, we normally use this in compiler design. Wherever we use trees, we make use of this threaded binary tree in place of a binary tree, and also we can make use of it for indexing in databases. Hope you might have understood the concepts of threaded binary trees well with this lecture. In the next lecture, we will learn about binary search trees. Thank you for